Hello class. On this video, we're going to start on chapter 3. Now, this is where things are actually going to start to get very interesting in terms of at least applications of linear algebra. And if you haven't seen linear algebra, you don't have to worry about that. I'll just introduce most of the things. But if you've taken linear algebra, that is a big advantage because you're going to recognize a lot of the things we talked about. Now, even though we're starting in chapter 3, we're actually covering 2 sections at once in the book. So we're covering, and write it here, covering chapter 3, section 2, and chapter 4, section 1. The reason I'm doing this is because section 4.1 is basically a more general version of what we're going to learn in 3.2. So I might as well just do everything in general. I think it's faster. In fact, I think most books just do it in general. So I think it's good. This is how I've done it before, and it works pretty well. So again, if you're following in the book, look at section 3.2 and section 4.1. Now, I've said this before a long time ago because the last couple of lectures were about face portraits. So being able to tell some information from a first order ODE and then not differential fields, but direction fields that gave us even more information of first order differential equations. And then I talked about Euler's method. Right? But before that, I said, so in terms of techniques we have for solving differential equations, we had for nonlinear differential equations, right, we had separable differential equations, we had exact differential equations. And then for first order linear, we introduced the integrating factor. Okay? Now, I said I did it this way because basically separable differential equations and exact differential equations are the only nonlinear methods that we're going to see to get exact solutions. Right? So starting with integrating factors, and especially now in chapter 3 and 4, we're only going to be focusing on linear differential equations. We're going to focus the heart of our study to linear differential equations, again, because the fact that they're linear allows us to use all this information from linear algebra. Okay? I'll make all of this precise later, whether it is through homeworks or through lectures, so don't worry about it. Just note that the fact that we have linear differential equations, they allow us to use techniques from other areas of mathematics that actually help us to learn a lot about these differential equations, okay? So just a small introduction of what we're going to be doing. So right now, I'm not going to be introducing solution techniques immediately. I'm going to be introducing just properties of differential equations, of linear differential equations, things that we can tell from them given that they're linear. Okay? Let's start with the first thing. Right? So consider an nth order, I don't know why it says an nth order linear initial value problem. Right? So nth order means that we have up to an nth derivative. Linear means that all of the coefficients of each derivative is an expression only involving x and constant, so no dependent variable y involved there. This a0 should also be of x, so I apologize about that. Okay. So we know that this is how an nth order linear differential equation looks like. Right? We've seen that before. And it's an initial value problem. Right? So if we want to, as I mentioned, I spent a lot of time on this in previous videos, that we have an nth order differential equation. In general, you're going to have to integrate n times, which means you're going to get n distinct constants of integration, which means if you want to get rid of them, you're going to need n initial conditions, which are given here. And they're initial conditions, again, because they're all at the same input value. Once you start to change the input values, let's say at least one of them, let's say is some other value x1, then it becomes a boundary value problem. But as long as all the inputs of these conditions are at the same input value, then it's considered an initial value problem. And I mentioned most of the time this initial input x naught is the start of the system. So if it's time, it could be time equals 0. Not necessarily the case though, but most of the time it is. So this is nothing new. I'm just reminding you how an nth order linear initial value problem looks like. Okay. Now, if you remember in section 2.4, we were talking about existence and uniqueness. So there were 2 theorems we saw. both for first order differential equations. One for linear first order differential equations, which was the easiest one to use and the one that gave you the most information, and one for nonlinear differential equations. The one for nonlinear ones, we have to find partial derivatives, we have to work in the xy plane, so things that you actually haven't learned precisely because you haven't taken Calc 3. But I mentioned this because if you remember, the linear one was very easy to work with and it gave you a lot of information. This actually generalizes to any nth order linear differential equation. So the fact that make that theorem easier to use is not that it was a first order differential equation, but that it was linear. I can see a bunch of typos. That should be a sub 1. Okay, so, oh, and actually before I start this, let me mention something else. We're skipping section 2.8 because I basically talked about 2.8 in section 2.4. That's this theorem I was talking about existence and uniqueness of solutions of nonlinear first order. And so that was section 2.8, so I just combined it with 2.4. So we're skipping 2.8. We're skipping 2.9. This is about something called a, what's it called, like a difference relation, I think? Difference relation, sorry. It's basically a recurrence relation, right? It's another way for a recurrence relation. So there's some theory there about recurrence relations. You can read it if you want. It's definitely something that shows up, especially when you're doing, you know, algorithms like the algorithm we saw in Euler's method. You saw we had a recurrence relation. We're not going to cover it in class, so it's not necessary. But again, if you want to look over these two sections, especially 2.9, because I didn't cover that at all, you're free to do so. Okay? But for our purposes, we're skipping them. Okay? So nothing about these two sections other than what we covered in 2.4, you know, about 2.8, nothing else coming in either the exams or the homework. That looks like a 7, I'm sorry. Okay. So as I mentioned, we have a pretty easy theorem for existence and uniqueness of an initial value problem. Right? And it's basically the same thing that we did in section 2.4 for the linear case, but you just have to check more things. So notice that in this case, we have n different functions, actually n plus 1 if you consider the constant one, that are multiplying the derivatives. And we have one extra function on the other side that's not being multiplied at all by derivatives. So in total, we have n plus 2 different functions that are not the derivative y, right? And again, I call them functions. You can think of them as just expressions of x and constants, like I've said before, right? So when are we guaranteed that there is a solution to this initial value problem? And do we know that it's unique? And the same reasonings as to why this is important that I talked about in section 2.4, they apply here, so I'm not going to go over that again. Okay, so when does that differential equation have a unique solution or a solution at all? Well, I write down here each of the coefficient functions, right? So each of the a sub i's that were in front of the derivatives, and the g of x that was on the other side. Right? What do you have to check? Well, just find an interval on which all of these functions are continuous, and of course, that contains the input variable x naught, right? It's an initial value problem, so we want our solution to exist in an interval that contains that initial x value. Right, so find an interval where all of these functions are continuous and that contains the input for the initial condition. The only extra thing you have to check is that the function in front of the nth derivative is not equal to 0 on this interval. As long as those conditions are satisfied, you're guaranteed a unique, so not only a solution, but a unique solution to this initial value problem on this interval. So again, just similar to what happened in section 2.4, in the linear case, not only do we know that a solution exists on some interval, we actually know what interval it is. We can find it. So let's do a quick example. Consider the initial value problem, x minus 2, y double prime, plus 3y equals 3, with the initial conditions, y of 0 equals 0, and y prime of 0 equals 1. Now notice this is a second order, right, because there's a second derivative, linear, because the coefficients in front of the derivatives are just expressions either involving constants or the variable x, and whatever is by itself, It's only an expression involving x and constants, right? So this is a second order linear initial value problem because the conditions, and we need two, right? Because we're going to take the integral twice. We're going to need two because, because we're taking the integral twice, and since they're given at the same input value, they are indeed initial conditions. Right? So this is indeed an initial value problem. So find an interval centered about x equals 0 for which the initial value problem has a unique solution. Okay? By the working theorem 1, what do we need to do? All of the functions that are multiplying that derivative and the function that it's by itself on the other side of the equation, not being multiplied by any derivative, have to be continuous on this interval I, and the function that's multiplying the highest order derivative, in this case the second one, can't be 0 on that interval. That's all we need to check. Okay, so let's look at these. So given them the same names as above, this would be our a sub 2 of x. A sub 1 of x is 0 because there's no term involving the first derivative. Right? This would be our a sub 0 of x, and then this would be our g of x. So those are the functions we're working with. Okay? So let's go ahead and find an interval on which all of these functions are continuous and where a sub 2, the function that's multiplying the highest order derivative, is not equal to 0. Well, so the functions are, so we have them up there. I'm just going to list them here. X minus 2, a constant 3, and a function x. Now, all of these functions are continuous everywhere, right? So it's very easy to check that first condition that we need to find an interval containing x equals 0 on which all of these functions are continuous. Right? We can start with the interval just being all real numbers, right? Because again, all of these functions are continuous everywhere. You learned that in Calc 1. However, our interval has to be an interval for which this function is not equal to 0, right? Whatever function is multiplying the higher order derivative, we have to remove any place where that function is 0 from this interval. Okay? So when is the function a2 of x equal to 0? Well, you can easily check that just doing some basic algebra, right? a2 of x equals 0 implies x minus 2 equals 0, which of course has solution x equals 2. So we can't use this interval negative infinity to infinity because we can't include any x value where the function multiplying the highest order derivative equals 0. So we can't include 2, so we basically have a choice for two intervals. We can either use the interval I equals negative infinity to 2, right? Or the interval I equals, actually let me give them different names. Or the interval I equals to infinity. What interval do we choose? Well, if you remember, so I naught is out of the picture, right? Because it contains an x value where a sub 2 is 0. Okay. So which one do we choose between I sub 1 and I sub 2? Which one? Well, remember when we were talking about section 2.4, I said, well, you usually take the biggest one, whichever is largest. In this case, both intervals have the same size. So in terms of which one you choose, well, if there's no context to the problem, you can just choose any. It doesn't really matter. If there is context to this problem, oh, no, sorry, I have to be careful. Sorry. We can't choose, there's actually only one of them that we can choose. Right? Why? Because the interval also has to contain the input, or the input value, which is 0. The interval has to contain x equals 0. Only one of these two intervals contains the x value x equals 0. Right? That interval is I sub 1. Sorry, I was going to talk about something else. I forgot that we also have to, the interval has also to include whatever input we have in the initial condition. So I forgot about that part. So don't do that mistake. Okay? So because of that, I sub 2 doesn't contain x equals 0. It's out of the picture, which implies the interval is going to be so by theorem 1, we're guaranteed a unique solution that exists to this initial value problem on this interval. Now, we're not done. Why? Because this is asking for the interval to be centered at x equals 0. This interval is not centered at x equals 0, right? If you were to plot it on a number line, you would have 0 here, 2 here, is where the interval starts. And then, you have all this in here up to negative infinity. So it's obviously not centered at x equals 0. So let's pick the largest interval centered at x equals 0. What is that going to be? Well, the furthest away we can move to the right of 0 is 2. So if we want the interval to be centered at x equals 0, the furthest away we can move to the left of 0 is 2 as well, by 2 units. So we would go all the way to negative 2, and our interval. And again, this is a case where it would be good to write a concluding sentence, right, just to conclude all the work that you're doing, and I understand what interval you're using and for what you're using it for. So our interval centered at x equals 0, for which this IVP, initial value problem, has a unique solution. Well, we're going to choose the interval negative 2 to 2. It's centered at 0, and it's the largest one we can choose that is centered at 0. And that's basically how you find the largest interval centered at 0. Okay. Now notice there's infinitely many intervals we could choose. We could choose the interval negative 1, 1. We could choose the interval negative 1 half, 1 half. That are all centered at 0, but again, we want to use the largest one. And that's how you use this theorem. So very easy to use, because again, it's just continuity in one variable. The only extra thing you have to check is that whatever interval you choose doesn't contain the zeros of the function that's multiplying the highest order derivative. And of course, the interval has to contain the input of the initial condition. But other than that, we're guaranteed that a solution exists on this interval. We know exactly what the interval is. Remember, in the nonlinear case, all we would know is that there is some sub-interval of this, that for which a solution exists. Here, we know exactly that on this interval it does exist. So again, this all follows from linearity. It's not something that I can prove in this class, but the key is the fact that this is a linear differential equation. The order doesn't matter. What matters is that it's linear.